This morning we have talked about the Y-shape or the tree-shape network and the delta or pi-shape network. So this is a typical three-terminal network. And I would like to discuss how could we transfer this side to the other side, Y-shape to the delta or vice versa. So this is what we learned from the study this morning. And to make sure that those two kind of three-terminal network behaves equivalently to each other, we have to make sure that the current from each terminal should be identical, and the voltage between any two pairs of the three terminals would equals to the voltage of that between that pair of the transformed network. So we talk about the equivalent conditions of the Ty transformation. We have a delta-shaped that three-terminal network, which has three A terminal, point A, point 1, 2, 3, each with a current I1 delta, I2 delta, or I3 delta. And we have a Y-shaped three-terminal network, and also it has three terminals, 1, 2, 3. Thus, it also has three incoming current, I1Y, I2Y, I3Y. And we have to make sure the current goes into the corresponding point terminal, the same nominal terminal will have the same amount of current and the same direction. And we have to make sure the voltage between two terminal will equals to the nominal between the corresponding two terminals voltage. So the voltage must be identical after the transformation, and the current will not will stay the same. And we don't care about what happens inside, but we have to make sure that after the transformation that the current flows into the terminals remains the same, and the voltage between the terminals are identical. So this is the equivalent conditions. I1 delta equals to I1y, I2 delta equals to I2y, I3 delta equals to I3y, and the voltage between terminal 1 and 2 in delta shape equals to the voltage between terminal 1 and 2 and in the Y-shaped network. So on and so forth, we have these conditions. From these conditions, we have deducted several set of equations from the KCL laws, current law, Kirchhoff's current law, and from the Kirchhoff's voltage law, we can reach the other set of functions that describe the relationship between the terminal current and the voltage over two terminals. And we also have this additional work which comes from the KCL, Kirchhoff's current law, by applying to the center point. Looks that we see that in delta-shaped network we do not have a center point, but in the Y-shaped network we have a center point. So we apply KCL to this point, then we reach this equation. So now we have two set of equations to describe the relationship between the terminal currents and the voltage between two terminals. So we have to make sure after the transformation, the corresponding current, and the corresponding voltage remain the same. So from the second set of equation, we have this relationship of equation set of three, and combine it with the first set of equation. You see that this equation could divide it into two parts, and also this one is divided into two parts. So this one describes the relationship between the terminal current and the voltage in the Y-shaped network. And the second one, the first one, described the relationship between the voltage and the current in delta-shaped network. That's it. So we can compare equation set 3 to equation set 1. Then compare them, we can reach the conclusion that R12 equals to R1 plus R2 and plus the product of R1, R2 over R3, so on and so forth. So it's very easy to remember. You see that we have the number 1, 2 at the bottom, and we have 1, 2, 1, 2, 3. So those two numbers, 1, 2, must each occur twice, and the rest one that didn't show in this bottom will come as end. So we can see that R23, we have 2 and 3, 2, 3, 2, 3, the rest one are 1. And we have R31, 3, 1, 3, 1, we have R2. This is how you're gonna remember that. But if you can remember that, it's not a big deal. You can just find it and use it in the textbook whenever you need. Or we can transform it into another case, like this one. Oh, that's much better. You see that it's better. It's much more succinct. So still we can remember it with a trick: 1, 2, 1, 2, 1, 2, 3, 2, 3, 2, 3, 2, 3, 1, 3, 1, 3, 1, 3, 1, 2. So the number that didn't disappear in this place only occur at the bottom of this bar only once. So that's how we're gonna remember that. But if you can't remember that, it doesn't matter. But you have to make sure that you know this kind of relationship, and if you want to use this kind of a relationship to reduce your deduction process and help you to transfer your circuit into a much easier, a much simple one, we have to use this kind of a relationship over and over again. Also, we can have the result from a delta-shaped network to Y-shaped network. So the Y connection can be obtained from the delta connection. Still, we have the similar stuff. G1 equals to G12, G32, G12, G32, and this one that doesn't contain number 1 at very bottom and appear only once. And G2 equals to G23, G12, G23, G12, and G31. So you see there's no 2 in here. G3 equals to G31, G23, G31, and G12. There's no 3 in this corner. So also we can have another form of equation, but equivalent. We can remember it as R1, R12, R31, R12, R31, and this one that doesn't contain 1 as a corner only appear once. R2 equals to R23, R12. You see all this stuff contains 2, number 2. And we can see that R12, R23, and this one, R31, doesn't contain number 2, only appear once. The rest appear twice, each appear twice. This one appear twice, and this one appear twice. You see this? This one appear twice, and this one appear twice. Okay, similarly, we can see R3. R31 appear twice. R23 appear twice, and R12 that contains no number 3 only appear once. So this is how we get the relationship between the delta-shaped network and the Y-shaped network. This is how we're gonna solve it. So we don't have to memorize it in particular, but after several times of use, we probably gonna remember that, but we don't have to do it deliberately. So this result could be deducted from the original set of functions, and we could also reach this conclusion from the delta connection to Y connection transformation. So this result could be obtained from either way you choose. So all the other tricks all in our following examples are based on this transformation. So to remember this, right, we have this kind of a transformation from each other. So from Y shape to delta shape, you see, we have this set of equation. And from delta shape to Y shape, we have another set of equation. So we could remember that. So we see that the resistance with single number, you see, it occurs in the Y-shaped network. That's it. So we can we can draw those resistors in this network. So we have inner 3, R1, R2, R3 in the inner case, and the three rest triangular side lines, each with the double-digit number as a red bottom. So what if we have a symmetrical triangular or delta-shaped network? Then the conclusion must be very easy. For each set of resistance inside 3 times larger outside resistance requires to obtain the same effect to the outside world. So we have the principle that 3 times outside to the inside. So big outside and small inside. That's how we're gonna remember that. So this is a trick to remember that much more easily. So we have a brief note method to remember that. The resistance in Ry equals to the multiplications of adjacent resistance over sigma R delta. And or we can say that the conductance in the delta-shaped network equals to where the multiplication of adjacent conductance in Y-shaped network over the sigma of the conductance in Y-shaped network. So this is a trick to remember that, but it doesn't matter. This is strange stuff. Why it doesn't show very clear? No money. I don't think it. No money doesn't bother you to remember. So we have to notice that the so-called equivalence is valid only for the outside. Outside the and bottom of the terminals to the network. But for the inside, it does this equivalence does not stand. Well, because for the inside, apparently they are not equal. The numbers are not equal, and the structure is not equal. So we only have the equivalence to the outside world. But that's enough. Sometimes we only need to know how it responds to the outside world. We don't need to know exactly what happens inside, right? It's just like you are driving a car. You hit the button, hit the gas, and the car accelerates. You don't consider how your force conducted from your feet to the gas, and the gas translate kind of force into a force meter and translate signal into electrical signal. That the electric signal goes to the MCU, and the MCU contributes how much oil to the combustion chamber. That is too much. We don't consider that much. We only know that once we heat the gas, the car will accelerate. That's all. So the equivalence only valid is only valid for the outside world, but the inside we don't care unless we have to talk about the inside. And the other thing we have to remember is that is independent from the external circuit. So once you transform the delta shape into Y shape network, or vice versa, it doesn't matter what kind of outside circuit you put on, it will still behave the same to the outside board. So the equivalent circuit is definitely is independent from the external rest part of the circuit. So how can we use it? Why? So that's why we have to learn it. We learn it to use it. So the first application is to simplify the circuit. So we see that first example. First, we have a bridge we have a T-bridge circuit like this. How could we analyze it? Obviously, we see that there's two kinds of stuff inside it. Since we see that this is a typical T-shaped network, right? But also, we see that this one forms a delta-shaped network. Delta-shaped network. So we could transform this kind of stuff using delta-shape to T-shape transformation. So we transform this 1 kilo ohm, this 1 kilo ohm resistor and change it into this one. But for the T-shaped part, we can also transform this kind of a circuit. Let's see, the blue circle one is a T-shaped network. We can transform this part into a delta-shaped network. So remember the special relationship between the delta shape and the Y shape. Once we have a symmetrical, you see we have a symmetrical Y shaped and a delta shaped network. We can using the 3 outside, 1 inside structure transformation to transform it. And you see this is a 1 kilo ohm, and this one is 1/3 kilo ohms T-shaped stuff. So if you choose the right corner, red circle transformation, we choose to transform this delta-shaped network into the T-shape, which means we change the outside. You see, from the last page we know that if you have a symmetrical stuff, right? Which means all the resistance in every branch are the same. So we're using the 1, 1, 1 inside, and 3, 3, 3 on the outside. So obviously, if you choose the right circle delta network, so it's using this 1 to 3 ratio transformation, where we can transfer that into T-shaped network. And we can see that we transform our 1 kilo ohm into 1/3 kilo ohm resistor. And also, if you choose this T-shaped network as a bottom, we can just transform that into this kind of a pi-shaped or delta-shaped network. And since its inside is 1, and so we can transform that into 3 kilo ohm. So 1, 2, 3 visual. Do you follow? Do you understand right now? Fahad, do you understand? Fahad? Okay, so we can continue. This is how we transform the Y-shaped network into the delta-shaped, and the delta-shaped into the Y-shaped. This case is very unique. You see that we don't encounter a symmetrical delta-shaped or Y-shaped network all the time, but what we did, we do encounter T-shaped network or delta-shaped network, but usually they are asymmetrical. So we have to use that the set of equations we have achieved before to calculate the corresponding values of the resistors after the transformation. So you can see that this is a demonstration. We can just see that in this case we have a lot of T-shape. You see, this is a T-shape network. That's another T-shape, and we can also transform this stuff into delta shape. So this is one method to do it, but actually, way it doesn't matter. And if you don't want to do that kind of transformation, you still can apply KCL and KVL, and also that could lead you to the right path. So this trick did help you a lot, but if you don't need the trick, it's not a big deal. You still can achieve the right result without tricks, but that will put extra labor in your calculation process. So after the Y-shaped and the delta-shaped connection and their transformation from each other to each other, we now talk about the ideal current law and the ideal voltage law and their connection in series connection or in parallel connections. So this part is relatively simple, much simpler than those the stuff. And see that if we have several for this example, we have two ideal voltage source attached to each other, head to tail, in a series connection way, and we can replace those two into one single voltage source, and the value of the transformed voltage source equals to the addition of those two form ideal voltage source. So if you have a series ideal voltage source connected head to tail together in a series way, and you can just transform that into a single one, a single voltage source, which has the value of the combination of all the voltage source combined together. But if you have several identical independent voltage source or ideal voltage source, and just put them together in a parallel way, we can replace them with one single voltage source, ideal voltage source, with the same amount of voltage it has. Because we have learned from the connection with series connection and the parallel connections, we know that in parallel connections, the components who share the same ends, those branches will have the same amount of value of voltage. So, which means one ideal voltage source here is enough. The other one is abundant. It doesn't work. So we can just cut it off and reduce this circuit into this one. But if you have a voltage source like this, for example, we have a 7-volt ideal voltage source, and it's paralleled connected with a 5-volt voltage source. What happened? Could that work? Of course not. If we are dealing with the ideal voltage source, the two ends of this terminal, the two terminal, must be constant. So it could only be one certain value. So you can put two ideal voltage source with different values and attach them in a parallel way with nothing in between. You can do that because that can create paradox, which means U equals to 5 volt. And in the meantime, U equals to 7 volt. It contradicts to itself, so that could not happen. But if you put some extra resistor in it, that could stand. But you can't put two ideal voltage source in a parallel way with nothing in between. And those two parallel attached voltage source with different value, that is not acceptable. We don't do that, since we create a paradox. Okay, this is Razim Ali Khishiti. Anyway, it's kind of it's difficult for me to pronounce your name because it's a Western name we're very familiar with because at least we will speak English, right? But the Islamic name we are not very familiar with, so it's hard to pronounce it correctly. So if I pronounce your name not right, incorrect, doesn't matter. We all accept that because my inability to recognize your name and pronounce it correctly is due to the sort of background knowledge of Islamic culture. So okay, okay, that's okay. I suppose every student have a Chinese name, right? Mm. So this is how we deal with the series connection of and the parallel connection of the ideal voltage source. So it's simple, but it's very important because in the latter case, lectures we're gonna use this skill all over again, over and over again. So to remember that only the ideal source with same value could be attached in a parallel way uh, with nothing in between. Otherwise, you have to uh, put some other electrical components between them. So in order to prevent the paradox. This is a English version of this page. But I think we don't have to go all over again. Uh, that situation we have explained. I think it's not very difficult to understand. So do remember this. The only the voltage source with the same value could be attached to each other with nothing in between in a parallel form. To remember that. The rest part is simple. You can see that you can just add them up and reach a new one. So it doesn't matter. So let's talk about the connection of the ideal current source in series or in a parallel connection way. So if we attach several ideal current source and put them together in a series connection way, we can replace it with a single ideal current source. So this is how we deal with it. And this value equals to the sigma of all the values of the current source. So we add all these current in each branch, in each branch, and we add them up together. We can reach the equivalent current source value, and we don't have to deal with all this stuff, complex stuff, all these extra branches. We only have to deal with one single branch with one single ideal current source. Similarly, similar to the voltage source parallel connection, only the voltage source, current source with the same value could be connected to each other at to tail in a series connection way. So only the current source with the same current can be connected in series. Otherwise, it will also create a paradox. So if you put, for example, if we put two ideal current together, and one is of 5 amp, the other one is 3 ampere. So in between, the current must be 5 ampere, and also the same current must be 3 ampere, which is a paradox. It could not be both. So we cannot, we don't allow that the current source to be connected in series values. So if you want to connect it, if you want to connect the ideal current source in series, we have to make sure they have the same value of current. So otherwise, it will generate paradox. So this is how it should be noticed. For example, the first example, let's see we have an ideal voltage source on this branch, left branch, and we have a ideal current source on right side, and they are connected in parallel. Could we transform that into one single voltage source? Could we? Because we know that the current is only affected on this branch, but the voltage in this between terminal A and terminal B, between point A and point B, will always remain US. So to the outside world, it looks the voltage will never change, but the current could change according to what kind of stuff you attach to it. See, like this, if you attach a resistor here, its current would be, if we have a resistor value R here, its current must be US over R. So it doesn't seem this current voltage, this current source works anyway. So it's redundant. We can just replace it. So we can transform this network into this one, because no matter what kind of stuff you attach to it, that components only have certain voltage of US, and its current got nothing to do with the current source. So in our analysis, we can't just reduce it. We can just cut it off. So if we put an ideal voltage source and the ideal current source, and we connect them in series, or similarly, we can transform that into a single current source. Because to the outside world, the current will remain the same no matter what kind of stuff you attach to it, but the voltage could change. So this voltage source is actually seems to be redundant. So we just reduce it. So by using the connection of the voltage source and the current source in series and parallel, we can simplify the circuit. And obviously, the first application is to reduce the redundant sources in the branches. So that did helped us a lot in simplification of the circuit. So the third case, see if we have a circuit like this, part of the circuit like this, and you can see that in this loop, the first loop, the current is always the same. And in this loop, you see that we have to consider that between A and C, the current, the voltage is always the same. So how could we just simplify it, right? We have to use the method from example 1 and example 2 to achieve that simplification. See, no matter what you did, the current in those two branches will be the same. So will be the current runs through the point C and point D. So no matter what kind of stuff you put on it, the current will not be changed, right? So it seems that in this case, the voltage source should be redundant. But also, we see that we can not just reduce the voltage source and cut it off, but it doesn't seem to be working. So we see what doesn't change is the current. So we can replace those four and simplify it into one single current source. And we see that between point C and point D, only the current will not change. Right? From KCL, right? We list the KCL equations to point A. We see that IS1 it goes away from the point A, so we give it a negative sign, and plus IS2, since IS2 goes in it, and we can see that minus IS, see, so we see that IS goes out of it equal to 0. So we know that I is equal to the subtraction of S1 and IS2. So IS equals to IS2 minus IS1. Do you follow here? Do you follow? So let's take a 10 minutes break. So from these three examples, we learned about how to reduce the extra or the redundant sources, independent sources in the circuit. And next, we're going to talk about the voltage source and the into current source, or vice versa. Actually, if we have an actual real voltage source, we know that for any voltage source, it contains a resistance, right? We don't have a voltage source that contains no resistance. But mathematically, we have assumed that the ideal voltage source is voltage source that contains no inner resistance. So we can recreate the characteristic of the real voltage source by put an ideal voltage source with a resistance and put them in series to represent its characteristics. So this kind of a branch represent how it behaves like an actual voltage source somehow. So we can do it like this. So from the outside view, we can see that the voltage source over the two terminals is then the ideal voltage source value, and it could change according to the current. So if we have a larger current and then the more voltage is consumed by the inner resistor and the less voltage is produced for the outside network. So this is how we represent actual source with mathematically assumed independent voltage source, ideal voltage source, and inner resistor. And the other one is equivalent transformation of voltage source and the current source. So in this section, we're going to talk about how to transform the voltage source into a current source, and how to transform a current source into a voltage source. See that we have a actual source look like this with a ideal voltage source combined with a resistor in series. We know that the outside voltage equals to US minus RI times I. And if we attach a resistor to the two terminals of this branch, then we can its actual external characteristic curve like this. So either we can see this is a function of a line, a straight line. From mathematical background, we see that we already know that. And as the current I increases, the U value, the value of U drops. So we could allow that actual source working at some point on this line. And its section on this axis is the value of the ideal source. So the ideal source value is the point that this line crossed with the axis U. And after we talked about how to represent extra voltage source, then we could go to the actual current source. So extra current source, we can represent it with ideal current source and with a resistor or conductor in parallel connection with it to represent ideal actual current source. Since the difference between the actual current source and the ideal current source is the latter has no the former has no inner resistance or inner conductance. So we could using this connection of ideal current source combined with a parallel resistor to create a similar characteristic curve to a real current source. So from the outside view, we see that it will have a current I equals to Rs minus G1 times U. U is the outside voltage. Also is the voltage on the conductor's branches and the voltage on the current source voltage branches. And we know that the conductance of the current source, inner conductance, is actually very small. So sometimes we just neglect it, but to represent an extra current source, we have to leave it here. So we can see that we can calculate its characteristic curve by list is the relationship between the outside current and the current source. Still, it's a line to represent it. We see that the crossing point has a value of Is, which is value of the ideal current source in the left branch, and as the outside voltage U goes up, and the current I decreases. So we have two models to represent the extra current source and extra voltage source. Now we're going to talk about the equivalent transformation of power supply. In this section, we both have we will have two kinds of ideal real source, voltage source and extra current source, to do that equivalent transformation. But that so-called equivalent means that the terminal current and the terminal voltage remain the same before and after the transformation. Just like what we did in the delta and the Y-shift network transformation. It's only what we mean equivalent only means only the terminal current and the terminal voltage. But what happens inside, that is not what we care about. So this is that. First, this is a mathematical model of a real voltage source. And we have the relationship between its voltage and current. So we can replace it and transform it into a real current source. So we have to make sure that the voltage between point A and point B to be the same, and the current between that runs to the terminal A and the terminal B has the same value. So combine those equations, we can have these values. So we have this equivalent conditions. The current source value must equal to the ideal voltage source over its inner resistor, and the conductance of the current source must equal to the reverse of the resistor resistance in the voltage source. So the first one is voltage source. The second one is the current source, and their relationship must follow this one equivalent condition, so they can be called equal. And it's only equal from the point of view to port A and B, AB port. But on the left branches, from the inside view, those two are completely different circuit. So, but we don't care about that. To let's say let it behaves to the outside world constantly. That's all. So we don't care about what kind of stuff you put inside that. We only need to let it work the same. This is the basic perspective we have. So we can convert the voltage source into a current source. And also we can using that relationship to convert a voltage source into a current source. So we know that GI equals to GI times RI equals to 1, right? GI times RI equals to 1. And the IS equals to US over RI and US equals to IS over G1 GI. So to remember this. So this provides us another trick to do the transformation of the circuit. So all these times we have learned all these tricks helps us to transform a complex, complicated internal circuit into a simplified and very succinct lucid chart of a circuit, and it does help us a lot to explain what happens in the circuit much more easily. So let's see that the directions. The direction of the current direction of the current source is opposite to the voltage direction of the voltage source. This is one thing we should pay attention to. And also, the so-called equivalence is only to the external circuits, but to the inside circuit, internal circuit, is completely different. Two kinds of stuff. And we know that there's no current flowing through the I in the open voltage source. An open circuit current source could have current flowing through the shunt conductance GI. So once you cut this, so there's nothing in between the points. So the only loop is to go this loop to let the current from the current source to complete a circle. We also know that without a circle, there's no current. So we have to make a complete loop. Once you connect it to a wire, and then we can just short circuit the conductance GI. We can do it both. And also, when the voltage source is short circuit, there's current runs through resistor I, and when the current source is short circuited, there's no current in the parallel conductor GI. So it looks like you just short circuited GI by bypassing it with a wire. Since the wire has no resistance, so its conductance equals to infinite. So there's no current to run through GI. If you put a wire and bypass the GI. And we also know that the ideal voltage source and the ideal current source cannot be converted to each other. So from the inside view, those two kinds of circuit is completely different. So now we could talk about the applications of the transformation of the sources. So we can just using power supply conversion by the circuit. So look, if we have this kind of a circuit first, example one, we can replace it into what kind of a circuit? We see that if we have this kind of a stuff here, we can just you see this to this point and this point is connected by a wire. So it's this dot A and the point B actually is the same stuff. So the same port. So we can just we say that rechart the diagram into this. Right? This is 5 ampere. This is a 2 ampere. This is a 3 ohm. This is a 4 ohm. And those two are connected to a 7 ohm resistor, right? So we can transform this into, so you see that this is a conductance parallel mounted with a current source. We can just replace it with the voltage source in series connection with a resistor. And so we can do it to the rest part of it. But we see that the upper part, this circle, we can replace it with a 12-volt voltage source, and in series with a 3 ohm resistor. And the lower part, we can just, you see this 2 ampere and 4 ohm. So we can replace it with a 2 times 4 equals to 8 volt. And a 4 ohm resistor. Those two are connected to this point A, right? So, and then they are attached to the 7 ohm resistor. And we combine the 3 ohm and 4 ohm resistor, then we have a 7 ohm resistor. So we can calculate that the current runs through the 7 ohm resistor is half ampere. Do you copy? Will you follow this? In this example, we use the trick to transform the current source into a voltage source. So by doing so, we reduce the list of several equations of KCL and KVL equations, and we don't have to solve that. So that indeed helped us a lot, right? So this is how we apply this. So every single stuff in this lecture, they have some use in some place. So this is actually is half theoretical and half engineering practice. So from our industrial background, we know that how to do that and to simplify the analysis and to reduce the labor of calculation. So this is the first example. The second one, you see that we have they are both on this 5 ohm that this is kind of awkward. You see that we cells together, and the other one has a voltage source. This is a 5 ohm resistor, so we can transform this into uh, a current source, and with a resistor in parallel connection. So we can transform the first branch into a voltage current source, and we have a 10 volt 5 ohm resistor. So 10 over 5 is 2, and is in parallel connection with a 5 ohm resistor. 5 ohm resistor. And it's connected with a 10 volt and 6 current source. So this is the first step, right? And so in this case, we can just in parallel form. So since you asked, so I deliberately slow down the analysis. In the last year's lecture, we just do it very quickly, but I'm afraid that you're not have enough time to digest, so we have just to slow it down, slow the pace down a little for you to understand. So I think you understand how to deal with it right now, right? So that this is another example. So we have two examples to how to apply this version to simplify our circuit calculation. First one, we change the current source into the voltage source with a series connected resistor. The second one, we change the voltage source into the current source to in order to have a simple solution for the question. So let's see another example. This one we combine with So all this dot A and B and C are ground. So that those three are the same stuff, right? Right? Represent. So we see from the T-shaped stuff, right? So this the L-shaped stuff, right? What we should we do the delta and Y-shaped transaction, or we doing it another way? So we can try a new technique, right? One in series connect with R, so we can just put these two together and create. In this section, this symbol to represent what is all. You can see that. Don't like that. I just say that so is not correct, and can also so there's a problem with this rubber. You can't read this stuff. Oh my gosh. Doesn't matter. So it is the symbol represented a voltage source. So if we use this symbol or this symbol are both right, they both represent the voltage source. See how to do that. So we can transform this current source into a voltage source. So we can transform this into one. Is less and this could be less. So this two branches is equal to one of this one, and it's negative with R here, right? One and R here, and two R here, and two R here, and A R here. So this next step, what we're gonna do is to this is a series connection, so we can just replace them. We can just replace them. with a single
Lakshya, please explain it again.
which part,
Previous, which you continue.
which part do you don't understand?
Two are resistance.
Which two are register? Which one?
You you draw it.
Which two are I did write? I read several two are register.
Below part.
Below
Below
one,
part. Yes, this
which one? This one, this one is directly from this.
okay.
We didn't calculate any two are in here in this step. So which two are you don't understand?
Second example, RS, R, R2R, 2R, 2RL. This formula I cannot understand.
I don't quite understand your question. Could you write your question down?
Yes.
So any other questions for the rest of students? Does anyone else have questions or problems? Does anyone else have any problems here?
Lakshya, you are circle the red part, RISR circuit.
Which
Please
one?
repeat.
Which one?
This one you circle it on red color.
What?
Yeah, yeah. This part.
What do you don't understand about this part?
Okay.
So what you want me to explain to you about this, right? This part.
Yes.
What yes? Don't. Well, I don't need your yes answer. What I know, I would like to know exactly what you don't understand. The point. Which point do you don't understand? Which step? Could you list
Yes.
it?
I cannot understand it because my network is bad. So I cannot understand this point clearly.
But I don't know which point. This, from this diagram to the lower diagram, we didn't do nothing. We know that. Do you understand the point? We say that since those three ABC connect all connected, so we just attach them together. This part, do you understand?
Okay.
So we transform this diagram upstairs and transform it to the diagram downstairs to understand this process.
Okay.
So well, we didn't do nothing. We just transform two brushes in the radial into one series and voltage source with a resistor in series connection. Do you understand that part?
Okay. 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 We should continue this problem.
Resistor are here and source with value times R and it's connected with R directly. So we just connect. We just combine the two single R resistor into one two resistor. Do you understand this part? Could you follow?
Yes, yes.
So then we could just do this process in a reverse process. We just transform this kind of series connected to a resistor with the voltage source, and we transfer back to a current source with 2R, right? And this value is equal to as the product of SR and over R. So it's only half the value of the original S. So this is the third step that we deal with this stuff. And all this stuff down together. This is another two. This is the two we have, and this is the R have. This is the two we have. And then we have a R L. Yeah. And then we do the parallel connection of the resistors and do that trick again. Are in a parallel connection, so we can just replace them with one single resistor of value R. So we do this process all over again. See, we can just transform those two branches on the left and transform it into a series connected voltage source and resistor. So we have a voltage source and has half of S and so you see that those two are in series connection. So one single resistor. And then again, we just we can just write it like this. You see, we transform into a current source. And with S. And it copies the part. So we see that these two are combined with each other in parallel form connection. So we can just replace them with a single one, right? Single one with the value of R. So then again, we should so we have this kind of a funnel shape of the circuit. Right, so this is how we deal with it. See, you see that this is what we have as a quarter of as current source and resistor R and this R. So the rest part is simple. We just do the current source into this transformation again. Then we have this. So its value must be as R a quarter. So this final circuit is simple enough for us to solve it. So we don't have to discuss the rest part of it any longer. So in this example, we use the trick of voltage source into current source and the current source into voltage source. That trick all over again several times. So so each step we just reduce the redundant resistors in this network. But we could also do it another way. We just using, you see, we see this is a T-shape circuit, and also this forms a delta-shaped circuit. So we could also using the delta Y-shaped transformation to do this job again. So so much for today. If you don't understand, you can go over this lecture. I think somebody is recording it. You can student for the record and to go over that again. So much for today. See you next week.
Okay, sir. Okay, now class is over now.